Hello all, welcome to the subject of VLSI Design and Technology. This is Professor Meenakshi Pancha from Electronics and Telecommunication Department, Parvati Bai, Gyanba Muje College of Engineering. So today in this lecture, we have to see how to implement the shift register by using Vhdl programming. This is the last lecture of this unit number 1. In the next lecture, we will begin unit number 2. So let's see how to write code for shift register. The diagram shows the shift register, which is 4-bit shift register. The main use for the shift register is for converting from serial data input stream to parallel data output or vice versa. This is the main use of the shift register. In this, we are going to convert the serial data into parallel and parallel data into the serial. So for that purpose, shift registers are used. For the serial to parallel data conversion, the bits are shifted into the register at each clock cycle. And when all the bits are shifted in, usually the bits are 8-bit, and hence the 8-bit register can be read to produce the 8-bit data parallel data output. Here each bit is shifted by each clock cycle. When all the bits are shifted into the register, probably particular bit shifting the each clock cycle will be need, and there are 8-bit registers placed inside to the shift registers, and for parallel to serial conversion, the 8-bit register is first loaded with the input data, and the bits are then individually shifted out, and 1 bit per clock cycle on the serial output line. To convert the data, parallel data into serial, first 8-bit shift register is placed to put the 8-bit data at a time, and at individually clock cycle, each bit is shifted serially. Hence, the output will be appear in a serial. And let's see how to write the code for shift register here. And first, we have to begin the coding with the library. So the library IEEE and use IEEE.std underscore logic underscore 1164.all. It should be mandatory. These two lines should be execute first, and then write entity. The name of entity we have given here shift register. So entity shift register is. So we are going to writing the code in a which form here. In this, we are going to write the code by using structural and behavioral modeling. Two methods are using here to write a code. So let's see the port declare, how to declare the port here. What are the inputs here? The clock is necessary for synchronizing the operation, and serial output data, the serial output data, and DIN here given, and synchronous and asynchronous parallel load is also there, and clock enable signal is also there, and serial or parallel output are these are things generally used in the shift register. So let's see the port here. Particularly, we are declaring port D in and clock. These two ports are input, and in STD logic, so we have mentioned in by using in STD logic, and Q is a single output, that is we have mentioned as a out STD logic. This is STD underscore logic is the data types, and end shift register we have to end the name of the entity with the name of the entity. Here our entity name is shift register. Then we have to construct architecture for this particular entity. So architecture example to the shift register is begin. Here we have to start with the begin, redefine word begin, and then we have to process on what signal the operation will be takes place. So we have to declare those signal in a process. So process and bracket clock and DL. Using these two input signals, the data is going to be processed and producing the output. So now we have to declare the variable here. So variable tmp here is nothing but underscore std logic underscore 3 down to 0. Here which type of input is there? Here parallel input or parallel output is we are going to. So variable we have to declare dtmp underscore logic underscore the vector form is there. So that is 3 down to 0. This is the variable. We have to mention the variable inside because inside the signal will be flow and there are four register are there. Hence we have to mention the variable and how the data will be flow into this particular register at a single clock. So we have taken variable 3 into 0, 3 down to 0 here. Then we have to mention how the variable will be flow. So let's begin and how to mention, and if we are going giving if condition here, if clock event and CLK clock is equal to 1, then only the d temp will be assigned, the variable will be going to assign do down to 0 there, and the Q output will be third output of the this temporary variable here. See here some bit will be here, some bit is stored in this register at, and we are going to inserting the here data into the register. Now this one is D1, so this one is D down to 0. So we considered like that it's 1 0, it's 0 1 2, and this one is 3. Serial in and serial output. The output is available at particular clock cycle. So at particular clock cycle, the data will be come here. If 1 0 will be, if 1 0 low signal will be available here, then this one bit is shift here, and this one bit will be shift here. This one will be shift here, and what is the one is available at, that will be produce output. Now this 0 is become here. So what the data stored in the register, that is 0 1 1 1, this is stored in the register, and this D3, this D3, this temporary here D3, this D3 bit will be now available at our output. So Q is equal to that, this temporary data, temp variable data D3 is available at the output. So like this the operation will be carried out. So if clock is 1, so at clock event is present and at clock is 1, then only the each bit will be going to shift. So hence the data, now the data in a temp 2 is presently this much up to 2. This much if data is into present now. Then the Q output will be here. So and if we have to end the if by using and if and process and the example. This and the example is the name of the our architecture. Here we have given as the architecture example for this entity. Entity name is shift. So this is the one example how to write the code 4-bit shift register. Now let's see another example based on this shift register only. Now here we will take 8-bit shift left register with the positive edge clock. Now let's see. Now let's see another Vhdl code based on 8-bit shift register that shift the bits by using at the positive edge of the clock, and which is in the form of serial input and serial output. So the data should be input serially and pass the data and shift the data in serial form, and output should be available in a serial form. And let's see how to write the code. The serial and serial output shift register delay data by 1 clock time for the each stage. So they will store a bit of the data for each register. A serial in and serial out shift register may be 1 to 64 bit in a length, longer if the register or packages are cascade. So let's see library. First we have to mention the library. Then after that write the entity, and we are going a shift register and giving a name as shift underscore SIS. That means serial input, serial output. Like that we have given a name for that. So let's assign a port. For every clock cycle, the data should be going to shift. So clock is one of the input signal, and the data is in a sign. So sign underscore std. There are two serial input. S in is nothing but serial input. There are two input terminal, clock and serial in. So both are in, and data is in a std underscore logic data type. And one output is a serial output, that is the mentioned as out, that under std underscore logic, which is also this data type, and the entity with the name of the entity, that is shift underscore siso. And we have to construct architecture for the entity. So we have given architecture name, that is a behavioral of the shift underscore siso is nothing but we are going to writing a behavioral code, behavioral model. So I have given the architecture name is behave, BHAV, and of for what? For shift underscore siso entity is. So I am declaring one temporary signal here. So in the behavioral, the signal should be declared by using predefined word signal. So signal temp underscore std underscore logic vector, which is 7 down to 0. Here 8-bit serial register is there. So signal will be flow 8-bit. So 8 particular input of the register we will consider as a particular signal is there. So that is 8 signal will be flow there. So output is also temporary signal will be assigned in the 8-bit form, that is 7 down to 0. Then we have to begin the process constructing the architecture and process on the clock. The device will be processed on the clock. So process the clock and begin again. If we are giving a condition there, if clock event is present and the clock pulse is 1, then only for I in 0 to 6 loop. Here there is a loop we are going to mention. For I is the number of times the data will be repeats here. So for here is 8 bits, so 8 bit time 8 times the same code will be run. So I in loop. So loop is start from 0 to 6. So loop, then temp I plus 1. So after temp, the temporary temp will be increment by 1, and which is assigned to temp I. What is the value of I should be increment by 1 and it's stored in a temp I. Then what is the temp I value, that will be stored in a temp I plus 1. Then and the loop, then temp 0, that will assign as a serial input, and whatever the values will be S in, that is the value of temp 0, in that the data will be stored there, and end the process. And what is the output of the uh, shift register is, that is the 7th bit of the temp, because they are using 7 0 to 7, 8 register is using there here. So total there, how many? 1, 2, 3, 4, 5, 6, 7, 8. So total there are 8 registers there, and here D input is giving and clock is also giving, and the output of each will be input of the register. Here output of the each will be input of the register. Yeah. Yeah, this is the clock. So these are the signal that is from 0 to 7, 0, 1, 2, 3, 4, 5, 6. This one is 0, sorry. So 7, this one is 7. From this is 0, this one is 7. So the 7th bit is the S out, serial out is the temp. Here temp is a variable. We are going to assigning this bit into the temp. So that's why we are here taken the temp variable assigned as a std 7 down to 0. 7 down to 0 is nothing but 7 to 0. Total 8 bit is there. So at a particular clock cycle, the each bit will be shifted, and the sin is will be sin is equal to temp 0, and it will incremented, and the 7th bit will be the output. So this is the way the 8-bit serial shift register will be work. There are many shift register is there. It is serial in parallel in, serial out, shift right, shift left. Similarly, we have to write the code. Now see how to write Vhdl code for counters. So let's see, there are two types of counter, up counter and down counter. An n-bit binary counter can be constructed by using modifying n-bit register, where the data input for the register comes from an incrementer or adder for an up counter, and starting with a value stored in the register, and to get to next up count sequence, we simply have to add 1 to 8. So if we want to count the value from 0 to 9, like a BCD values, then we can say BCD counter, it will start counting from 0, and after counting it will add increment one number, and it will count 0, 1, 2, 3 up to 9. So like that the counter will be going to add. So adding number 1 at the each step is which means that it's counting the number up direction, hence it is called as an up counter. And there are another counter which is a down counter here, which is bit starting from highest level. From that they decrementing the value by uh, each by one number, and which will decrement and then count. So that is called from for example, start if BCD down counter is there, it will, if it is started from 9, then it will -1 and 8 -1 7, like that it will decrement the value and then count up to 0. That is a down counter. So we have to write or construct, we have to write VHDL for the we have to implement the VHDL code for up counter here. The particular number of bits is nothing but there is a that much of bit counter is the 4-bit counter. The n-bit binary counter, the n-bit, if it is a binary counter, then n-bit binary counter will having n-bit register. So if we are going to 4-bit binary counter, we are going to construct, there will be a 4-bit register will be used. Registers may be here used. So 4-bit binary up counter with the asynchronous clear. And let's see how to write the code for this. The behavioral VHDL code for 4-bit binary up counter. Here the figure shows the binary up counter. The statement here used IEEE.std underscore logic underscore unsigned dot all is made in order to perform the addition of the std underscore logic underscore vector. So on that data type, the addition operation should be performed. For that, we are going to using the data type use we are going to using the statement or library use as IEEE.std underscore logic underscore unsigned dot all. So here count, clear, clock are 3 input is there, and one output is there which is in a vector form, because this is a 4-bit binary vector. Then it's a vector form like a 3 down to 0 we are going to using here. So let's see. Let's define the library first. Library and use IEEE.std underscore logic underscore 1164.all. Then use IEEE.std underscore logic underscore unsigned dot all. Then std logic vectors, because the counter operation should be performed on the std logic operation. So std logic underscore vector will be used. So let's begin constructing the entity. So entity counter is the name of entity we have given here counter. So what are the ports is there? Ports declaring here inputs outputs. So what are the input signal is there? Clock, clear and count. Here clock, here clock, clear and count. These three are in std logics. These three std logic. And q is out std logic vector, that is 3 down to 0. Here out is std logic, that is a 3 down to 0. And no bits, that is number of the bits. 4-bit is nothing but 4 register will be used here, and which can be changed in the this line in the end of the counter. We can change this. Then after declaring the entity, then we have to construct architecture for that entity. We are going to writing the behavioral model. So architecture behave, this name of our architecture for counter. So of counter, we are going this construct the architecture of the entity. Name is counter there. Then here signal will be, we are going to use, there are signal will be flow inside the counter. So this is 4-bit counter, hence 4 signal will be flowing there. So the name of signal we are given like a 3 down to 0 here. The number 1 0 1 2 3 is there. Signal are there. So we have mentioned by using signal value underscore std underscore logic underscore vector 3 down to 0, and which can be changed in this line. So number of bit can be changed in this line. So after declaring the signal, we have to begin with the statement. Then we have to mention here process. The counter will be processed on the signal on clock and clear. So we have to mention here both. Then begin. If clear equal to 1, then the value assign 4-bit vector to 0 0 0. Whatever the input is there, and whatever the stage of the counter is there, if clear bit is then high, then the output value should be 0 0 0 0. So because the 4 bit there are 4 zeros there, else if the clock event and clock is 1, and then if count equal to 1, then the value will be assigned value plus 1, their variable value, and that which is going to assign 1 and plus it, each time the value will be going to assigning and incrementing by 1, and if we have to, because both the if condition we are going to use, first is clear equal to 1, then the output will be 0 0 0. If that condition is not satisfied, then we comes to else, then comes to that the clock event is there and which is high, then the count value will be, if count is 1, then the value will be going to increment by 1, and we have to add if by both the time, we have to write both the ends if, and end the process we have to mention there by using end process, and finally q is going to assign the what is the value stored in the variable value there. So q is going to assign value and end the behavior. This is the way of writing the VHDL code for the 4-bit up counter, binary 4-bit up counter. Similarly, we have to write code for down counter also. Similarly, we have to write architecture. Behave for the counter is, then the signal value, because there is a 4-bit counter is there. 2, 3, 4. This is a 4-bit counter. 4-bit binary counter. Initially, the value will be 0 0 0 0. At particular clock cycle, this will become 0 0 0 1. At the particular clock cycle, this will become 0 0 1 0. So like this, the counter will be operated 0 0 1 1, like this, 0 1 0. Like this, counter will be operated here. For that, the signal value should be assigned with the value, because of this is a 4-bit counter. So the value will be take 3 down to 0 3 2 1 0. So 3 down to 0 value should be there. How to mention by using predefined word signal value, and that can be changed. These values can be changed with the lines, the number of lines we are going to use. Then we have to start with the begin. So we have to start with the begin. Begin is a predefined word here, and we have to mention process because it's a behavioral modeling. So our 4-bit counter will be operate on these two signals, clock and clear, which will process on these two signals. So we should mention here in the bracket. Then we have to begin again. There are two conditions are there. If clear equal to 1, then only what will happen, if this is clear, if this clear is equal to 1, then irrespective of the output, it will not take any consideration of the output, what output present at the terminal. It will simply make all the output 0 0 0, which will going to assign the output is 0 0 0. If the clear is 1, then the value, what are the value, what are the signal value at the output will be going to assign like 0 0 0. 4-bit is a same as 0 0 0 0. Else, if the clock event is there, if this condition is not satisfied, if clear is not 1, if it is 0, then what will happen? Then if this is 0, then clock signal is there. So the clock signals are there. So if the clock is high, then if count is 1, then if the BCD count is 1, then what will happen? Value is equal to 1. Then what will happen? If clock is present at particular clock, it will going to increment 1, and which will going to assign to B. Yeah. So at particular clock pulse, this is going to assign like this. 3 plus 1 like this. So this is there are two conditions on that the counter will be worked, and we have to end with those two condition with the end statement. Then we have to end the model. We have to mention there end the model. End the process. And finally, the output Q should be assigned, and finally the output Q should be assigned by the value. So output finally Q should be going to assigning value. And we have this is the way of writing the program, the Vhdl. So similarly, we have to write program for down counter also. Let's see. This is the writing the code. Binary down counter. An n-bit binary counter can be constructed using a modified n-bit registers, where the data input for the register come from the decrement or subtractor for a down counter, starting with the value stored in the register, and to get to the next down count sequence, we simply have to subtract a 1 digit to it. The 4-bit binary down counter with the asynchronous reset. The behavior of VHDL code for 4-bit binary down counter shows in figure. The statement we are going to use IEEE.std underscore logic underscore answer dot all is need in order to perform a subtraction on std underscore logic underscore vector. So this is the starting the library IEEE use IEEE dot std underscore logic underscore 1164 dot all and use IEEE dot std underscore logic underscore unsigned dot all. Here this subtract and std underscore logic underscore vector, and the entity counter is the port clock in std logic. The name of the entity is a counter, and here the input is clock preset count, and Q is also available there. Here this figure shows these three are inputs and this one is output. The inputs here we have mentioned in the entity part: entity, clock, preset and count. Clock, preset and clock, these all are in STD logics, and there is one output. The output is a 4-bit output, and which is 3 down to 0. So we have to end the entity with the predefined word and which is name of the entity is a counter. We have to construct architecture for this entity. The architecture which is using behavioral modeling, and we are going to using behavior, and the name of counter, the name of the name of the entity is the counter. For that counter entity, we are going to constructing or writing the architecture. We have to assign the value signal flow inside to the counter, which is 4-bit counter, and we have to assign the signal value underscore std underscore logic underscore vectors, which should, because the 4-bit we have to use a vector which is 3 down to 0, and we have to begin the predefined word begin and process on. Because of the behavioral modeling, we have to begin the process, and what signals the output will be in the data, on what signal the input data will be processed, and how the output will be behave. So we have to mention in the process with by using a bracket. So there are two clear and clock signals are there, or preset. Here there are preset signal is there. We have to mention in the clock. Then we have to begin. If preset equal to 1, then the value should be preset. In previous program, in a down counter, we use clear. While the high signal on that clear pin, the output will be set to 0000. But what will happen in this preset, when the high signal occurs on the this preset, then what will happen? The output will be going to set 1111. So because this is a down counter, we have to set the forward maximum value to make it to count as down. So if if reset equal to 1, the output will be 111. If this condition is not, reset is not 1, then if a clock event is also there and clock is 1, then if whatever the count is there, the count will be going to set 1, and then the value will be going to assign value minus 1. So then we have to end with the statement of if, and because we are going to if conditions, we have to end the 2 times. So and if. So end the process, and finally the queue will be going to assign the values. So this is, and after we have to end the architecture by using the name of the architecture and the head. This is the way of writing the Vhdl code for 4-bit binary down counter. So similarly, we have to write the Vhdl code for both up and down operation, up and down count operation. So previously in two programs, we write up the program for particularly for up and down counter. So in this program, we have to write the code for both up and down counter operation. So we can design an n-bit binary up-down counter just like a up counter, except that we need both an adder and the subtractor for the data input to the register. The VHDL code for up-down counter here shown is similar to the up counter code, and but with the additional logic for the down signal. If the down is asserted, then the value is decremented by 1. Otherwise, the value will be incremented by 1. To make the code a little bit different, the counter output Q is declared as an integer that ranges from 0 to 16. So let's write the code. First, start from the library. The library IEEE use IEEE.std underscore logic underscore 1164.org, and start writing the entity, and the name of entity are given as up down counter or UD counter. U up down counter, UD counter, and is a predefined word. Then we have to assign the port here. Clock, clear, count down. So these are the input signals. The clock to clear, count down. There are 4 input signals. We have mentioned in std underscore logic. Then N1 output signal is that is count integer range from 0 to 15. Sorry, 0 to 15 we have to count here and end the UD counter is nothing but up down counter. The architecture behavior of up down counter is begin by process clock comma clear and variable value integer range from 0 to 15 begin. So here data should be processed on clock and clear and the variables are also there. We have to mention your variable values and integer range from 0 to 15 and begin. If clear equal to 1, then the value equal to 0. There is any clear into 1, then value can say to put into 0. If else the clock event is there and clock is 1, then if clock is equal to 1, then clock will put to 0. Whatever the value, it should be increment by 1. Else, this is not, if count equal to 1, the whatever the value will be present, it should be incremented by 1. Or if down equal to 0, then whatever the value is there, it should be decremented by 1. So we have to end with the and if. So we are using multiple if there, we have to end with a multiple if statement. Then finally we have to assign the output q, which will be the value, whatever the value is there, we should assign q and we have to end process and end behavior. This is the way of writing the Vhdl code for binary up down counter. This is enough for the day. Similarly, way all the code should be written. So this is the final lecture of the unit 1. In further lecture, we will be going to start with the unit number 2. So this is enough for the day. Thank you.